We've spent a good bit of time together discussing a wide variety of topics related to algebra. We're really in the home stretch of this course now, and I'd like to close out the course by spending a few lessons under the theme of where algebra meets combinatorics. Now, combinatorics is a branch of mathematics where we try to solve problems that typically start out with the question, how many of something are there? You know, how many different two-topping pizzas can you order at your favorite pizza shop? How many ways can you be dealt a full house in 5-card poker? How many different ways can you select the 5 starting players for a basketball team if the team has 12 players on it? There are lots of questions like this that we could pose. And over these last few lessons, I'd like to develop some mathematical tools to help with these kinds of questions. In the process, I want to show you some very close connections between this field I call combinatorics and algebra, which is what you and I have been studying now for quite a long time. Believe it or not, there are lots of connections between these two areas, so it's not going to be hard to convince you that these two mathematical subjects are related. To get started today, I want to introduce you to something called Pascal's triangle. Now, I would suggest that we start by building the first several rows of this triangle together. So, if you've got a piece of paper, pull it out, take out a pen or a pencil, and let's do this together. First, you're going to start with a 1 at the very top of the triangle. So you're just going to put a 1 all by itself. And then in a second row, you're going to put another 1 and a 1. So you should have at this point then a small triangle, if you will, a 1 on top followed by 2 1s underneath. Now, every row of this triangle that we build from here on out is going to follow 2 very important rules. First, the first and the last number in every row is going to be a 1, always for us. It's going to be a 1. And the other rule is that each of the other elements in the row is just the sum of the 2 numbers just above it. So if you've got this 1, 1, 1 already written on your page, then the next row is going to have 3 numbers in it, and it's going to be 1, 2, 1. Now, why is that? Well, remember, the first and the last numbers in every row are always going to be 1, so that's why we had to have the 1 at the beginning and the end. And that middle 2 is coming from the sum 1 plus 1 of the numbers just above the 2. So if you've written this in a nice sort of way, what you should now have is a slightly larger triangle, 1 on top, followed by 1, 1, followed by 1, 2, 1. Now, what would you do if you wanted to build the next row? Well, keep in mind, first of all, that it must start and end with a 1. And now there are going to be 2 numbers in the sort of middle part of that row. In this case, both of those numbers are going to be 3 because the 1 plus 2 is equal to 3 and the 2 plus the 1 is equal to 3. Remember, all the numbers in the middle part of the triangle are built by taking the sum of the 2 numbers just above. So your triangle now has 4 rows, 1 followed by a 1, 1, followed by 1, 2, 1, followed by 1, 3, 3, 1. Now from here, you and I should be able to build the next, I'd say 4 or 5 rows pretty quickly. So in fact, I would suggest you try to build up now to maybe a 10-row triangle using those same 2 rules. Always start and end with a 1 on every row, and every other element is just the sum of the 2 numbers just above it. So why don't you try to build the next, say, 5 or 6 rows of the triangle and see how you do. Okay, now your triangle at this point should look like this triangle. So hopefully you built up maybe 9 or 10 rows at this point. And let's say you got up to at least the row that starts out with a 1 followed by a 9. Then that row should have 1, 9, 36, 84, 126, and then another 126, 84, 36, 9, and 1. Notice how the numbers sort of grow up and then they go back down, if you will, as you read across the row, and they seem to be sort of copies of one another as you go. Now, the nice thing about building that triangle, and this is the important thing about Pascal's triangle that I want to share with you at this point, is that all you had to do was do little addition problems to build the next row as you built the triangle. You just had to add these two numbers to get this, and add these two numbers to get this, and then always remember to put a 1 at the beginning and a 1 at the end. And that was all you did to build that triangle, which means, in some sense, you just needed some elementary school level arithmetic addition in order to build the triangle. Now, before we go on to talk about the importance of that triangle, let me make a few historical remarks. First, this triangle bears the name of Blaise Pascal, who is a 17th century Frenchman who worked in a number of areas of mathematics. He's best known for being one of the earliest inventors of a mechanical calculator, and he worked on a wide variety of mathematics problems and physics problems during his brief life. He died at the age of 39. Interestingly enough, Pascal was not the first to study this triangle of numbers that we call Pascal's triangle. But he did write a very significant book entitled Treatise on the Arithmetical Triangle, in which he studied many of the properties of these numbers. He studied them extensively, and he showed how they could be used to solve lots of problems. So this triangle bears his name, although he wasn't necessarily the first person to actually study it. Now, let's transition to connecting Pascal's triangle to algebra. There was no algebra that you needed to build the numbers in that triangle. You just had to do a little bit of addition, a little bit of arithmetic. And after all, this is an algebra course, so somehow we should try to connect this triangle of numbers to some algebra. Okay, to make this connection, I want you to work on the following problem, which doesn't look like it has anything to do with that triangle, at least at the beginning. So I'm going to suggest you work this out yourself, and then we'll try to make some of this connection. Here's the example I want you to work out. Expand x plus 1 to the third power, to the power 3. In other words, I want you to multiply out x plus 1 to the 3. Now, notice that what you're doing is you're taking the binomial x plus 1 and you're multiplying it with itself basically 3 times. So you're doing x plus 1 times x plus 1 times x plus 1. And to expand that, you just want to pick 2 of the sets of parentheses, or 2 of the binomials, and expand that part, leaving the third x plus 1 alone. And then, once you've done that expansion, expand again with that extra x plus 1. So here's how I might do it. X plus 1 to the 3 is equal to x plus 1 times x plus 1 times x plus 1. And now if I just look at the first 2 binomials and multiply those out, I'll have x squared plus 2x plus 1, and that still needs to be multiplied by another x plus 1. Now, to get that all multiplied out or expanded, I have to make sure that every term in that trinomial is multiplied with every term in the binomial. And so that's going to give me actually 6 terms once I multiply it all out. And when I do that, I'm going to have x cubed plus 2x squared plus x squared plus 2x plus 1. And when I combine the common terms, the x squareds together and the x's together and so on, I will end up with x cubed plus 3x squared plus 3x plus 1. Now, I have a cubic polynomial in front of me, and I want you to notice that I can actually write it as 1x cubed plus 3x squared plus 3x plus 1. So I just can explicitly write the 1 in front of the x cubed if I really want. Now, I want you to look at that polynomial, but I want you to sort of hide the powers of x from your eyes. Or if you've written this down with a pencil, literally erase all the powers of x, the x cubed, the x squared, and the x. And I want you just to focus on the coefficients that are left. And when you do that, you'll be left with the 1 that was out in front of the x cubed, followed by a 3, and a 1. Now here's a question for you. Have you seen that list of numbers in this lesson? In fact, you have. It's one of the rows of Pascal's triangle. Is that a coincidence? Well, maybe, although let's hope that I know what I'm doing here as I teach this course. it turns out it's not. But just to convince you that it's not, let's expand one more power of x plus 1. Let's multiply out x plus 1 to the 4th power, and let's see what coefficients we get then. Now, to be smart about this, we would multiply out the x plus 1 to the 4th by remembering that x plus 1 to the 4th is the same as x plus 1 to the 3rd times an extra x plus 1. And you and I both know how to write x plus 1 to the 3rd now. We just did that a few moments ago. So x plus 1 to the 4 is the same as x plus 1 cubed times x plus 1. And the x plus 1 cubed is the same as x cubed plus 3x squared plus 3x plus 1. So what I really want is x cubed plus 3x squared plus 3x plus 1 times an extra binomial x plus 1. So now I have to get all the terms in that little binomial multiplied with all the terms in that 4-term polynomial. And when I do that expansion, I'm going to have x to the 4th plus 3x cubed plus 3x squared plus x cubed plus 3x squared plus 3x plus 1. And combining the like terms, I'll get x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. Notice I've got this polynomial written in standard form, just as I did in the previous example with the x cubed plus 3x squared plus 3x plus 1. Now it's in standard form. Hide the powers of x from your eyes or erase them or whatever you want to think about, and look at the coefficients again. And they're going to be 1, remember there's a 1 in front of the x to the 4th term, followed by 4, 6, 4, 1. Now look back at your Pascal's triangle again. That is another row. In fact, it's the next row down of Pascal's triangle. To be honest with you, this isn't a coincidence at all. This is happening for a reason, and it's happening because the powers of the binomial x plus 1 and Pascal's triangle, they can be connected to what's called the binomial theorem. So the coefficients that you see in the powers of x plus 1 actually really do come out of Pascal's triangle, and something called the binomial theorem actually proves it. Now I'm going to show you what that theorem says in just a minute. In fact, it says pretty much what those examples showed us. But before I actually show you the binomial theorem, I need to set it up with a little more mathematical notation known as factorials. So let me give you a definition of factorials very quickly, just in case you've never seen them before. So I'm going to let the number n, or the letter n, if you will, stand for a positive integer. So n is going to be a positive integer. Then n factorial, which is going to be denoted as an n followed by an exclamation point, is going to equal the product of all of the integers from 1 up to n. So an n followed by the exclamation point is said to be called the n factorial. So for example, n factorial, if you let n be 4, is the same as 4 factorial, which is 1 times 2 times 3 times 4, which is equal to 24 if you just multiply it all out. And something like 5 factorial, which would be written as 5 with an exclamation point after it, is equal to 1 times 2 times 3 times 4 times 5. And if you multiply all that out, you'll get 120. Now notice that 1 factorial is equal to just 1 because all the numbers from 1 to 1 are 1, and 1 by itself is just a 1. But I also want you to know that by definition, we're going to say that 0 factorial also equals 1. So don't lose track of that. 0 factorial will, by definition, also equal 1. We don't want to get into why that's true. It's just the definition for now. So 0 factorial is 1. Now, I can hear some of you saying, why in the world do I need these factorials? Well, that would actually be a very good question. It really is a good question. But let me try to convince you that they're important by completing the following example. I want us to simplify two different quantities. 5 factorial divided by a 4 factorial times 1 factorial. And also, I want to simplify 5 factorial divided by 3 factorial times 2 factorial. Now, to be honest with you, there's nothing fancy here. I just want us to walk through what would happen if we did these multiplications and then canceled parts of the numerator with parts of the denominator, just to see what numbers we get. So let's do both of them really quickly, and then I'll try to tie in what I'm trying to show you with Pascal's triangle. So 5 factorial divided by 4 factorial times 1 factorial is the same as just 5 factorial over 4 factorial, because 1 factorial is 1, so it's not going to help you at all in the multiplication. And now the numerator becomes 5 times 4 times 3 times 2 times 1, and the denominator is just 4 times 3 times 2 times 1. And now a whole bunch of cancellation will occur. The 4s will cancel, the 3s will cancel, the 2s will cancel, even the 1s would cancel if you wanted to do that, and you'd be left with just 5 on top divided by 1, which is 5. So the first example is just equal to 5 once you do all of the simplification. Now, let's try the other. 5 factorial divided by 3 factorial times 2 factorial. Well, that's the same as 5 times 4 times 3 times 2 times 1 in the numerator, divided by 3 times 2 times 1 times 2 times 1. The 3 times 2 times 1 comes from the 3 factorial, and the 2 times 1 comes from the 2 factorial. Now, do all the cancellation that you can see again, and what you'll end up noticing is that all of the denominator portions will cancel again, and you'll be left with just 5 times 2 on top, which means that this final answer is 10. Now, let me ask you a question. Where have we seen the numbers 5 and 10 in this lesson? Well, here's a hint. Go back to Pascal's triangle. This lesson is all about that triangle. And if you look at it, you'll see that there's a 5 and a 10 right next to one another in the row that looks like 1, 5, 10, 10, 5, 1. Could it be that these factorials that I've given you could be used to somehow write down a formula to calculate the numbers that are in Pascal's triangle without having to build them one row at a time? The answer to that question is yes. And let me reiterate why that question is so important. If I wanted to know, let's say, what one of the numbers in the 100th row was going to be, I would have to build that by doing all those additions with all of those rows the way you and I did the initial calculations on that triangle earlier in this lesson. What we're trying to get to now is a formula where we can actually pinpoint one particular value in the triangle without having to calculate all the ones above it. That's the goal we want to accomplish now with this factorial function. Now, to describe this formula that's going to help me pinpoint these numbers, we need to label the triangle in a very special way. Now, it's probably going to seem a bit odd at first. I'll give you that. But just bear with me as I explain to you how you actually want to label this triangle in just the right way. So the rows of the triangle are actually going to be labeled starting with row 0. So the first one that was at the very top of the triangle is actually in row 0. Then the 1, 1 row is going to be row 1, and then the 1, 2, 1 row is going to be called row 2, and so on. So for example, the row 1, 5, 10, 10, 5, 1 is actually going to be labeled as the 5th row. So the row number is actually the number after the 1 in that row, okay? Now, within each row, we're going to say that the 1 that's at the beginning of the row is actually the 0th element in the row. Then the next number in the row is going to be the first element in the row, and then the next one will be the second element, and so on. Now, with that notation, so to speak, or that setup, we can define a new function which we're going to call C of n comma r, and it's going to stand for the element in Pascal's triangle which is in the nth row and is the rth element of that row. So let's just try to make sure we're on the same page with this. C of 4 comma 2 would be the 6 that's in row 4 and is the second element of that row. Remember, the 1 at the front of that row is actually the 0th element, And then the 4 in that row is the first element, and then the 6 in that row is the second element. So C of 4 comma 2 is 6. Similarly, C of 6 comma 1 is also 6, but that's now down in the 6th row. C of 7 comma 3 is 35. C of 2 comma 2 is just 1. And C of 0 comma 0 is that 1 that's at the very top of the triangle. Now, you're probably saying at this point, that's the stupidest way to label those elements that I could ever have imagined. Well, it's not so stupid once you see this really cool formula for C of n comma r that we can write down thanks to the factorial function. So let me now quote for you a fact about how you could calculate the values in Pascal's triangle one at a time, no matter which one you wanted to calculate, without ever having to add the values from one row to the next to build the triangle. Here's the fact. If you choose n to be any number greater than or equal to 0, and you choose r to be any number greater than or equal to 0, and by number I mean whole numbers here, then C of n comma r, the element in Pascal's triangle in the nth row and the rth element of that row, is equal to n factorial divided by the quantity r factorial times n minus r factorial. Now that fact is huge, and I don't have time to explain how to prove that this is really the right formula, but we're going to use it heavily in the next few lessons. So you'll definitely want to set this formula to memory, that C of n comma r is n factorial over r factorial times n minus r factorial. Let me just suggest that we check to make sure we see how it works by trying two relatively good-sized examples just to make sure that the formula really does give us the correct values in Pascal's triangle. So I'm going to suggest you try this one for yourself and do the calculations, and then we'll see if we get the right answer. Calculate C of 8 comma 6. Now I'm going to use this formula, C of n comma r equals n factorial over r factorial times n minus r factorial. In this case, n would be 8 and r would be 6. And so C of 8 comma 6 is the same as 8 factorial in the numerator divided by 6 factorial times 8 minus 6 factorial. Now what does that give me? Well, start simplifying a little bit in that denominator and you'll realize that this is the same as 8 factorial on top divided by 6 factorial times 2 factorial. Now, let's just write this thing out and start canceling. 8 factorial on top is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And the denominator is going to become 6 times 5 times 4 times 3 times 2 times 1 times 2 times 1. That's the 6 factorial multiplied with the 2 factorial. And now you can see a whole bunch of cancellations. I immediately see that the 6's and 5's and 4's and 3's and the 2's are going to cancel. And I'm left with 8 times 7 divided by 2 times 1, which is 56 over 2, which is 28. Now, is that what you got? I hope it is. And now let's look in Pascal's triangle. We had the triangle built pretty large earlier. Look in row 8, keeping in mind that row 0 is the very top. Look in row 8, 6th position in that row. Again, keeping in mind that the first number 1 there is in the 0th position. And what you're going to see is a 28. 28 is what we calculated with that formula. And that's a great example then of how to use this formula to get one value of Pascal's triangle without having to do any other work above it. So that's a good thing. Now, let's try another example to see how this formula might be useful. Now, this is going to be a much bigger example than the one we just tried, but it's still a great example to show you how useful this formula is. I want us to calculate C of 100 comma 2. Now, I want you to let this soak in for just a second. If we didn't have this nice formula for C of n comma r, then you would have to calculate the first 100 rows of Pascal's triangle before you'd ever get to C 100 comma 2. That is a lot of work. And it's a lot more work than we really want to go through if I just want one value, c of 100, comma 2. So this formula is really, really helpful. Now you might be thinking, oh, but that's going to be a lot of work. It's really not. Let me walk you through it. C of 100, comma 2 is equal to 100 factorial divided by 2 factorial times 98 factorial. Now, think for just a minute about how to do this in a smart way, in a wise way. Notice that the 100 factorial is the same as 100 times 99 times what's left, which is 98 factorial. Because 100 factorial is going to be all the numbers from 100 down to 1 multiplied together. So rewrite the 100 factorial in the numerator as 100 times 99 times 98 factorial. In some sense, I'm just peeling the 100 and the 99 right off and putting them in the front. And what you'll then have is 100 times 99 times 98 factorial divided by 98 factorial times 2 factorial. And now notice the 98 factorials will cancel. So you don't have to do all that writing. You can just cancel those two things off. And you'll have 100 times 99 divided by 2, which is the same as 50 times 99, which is 4,950. It's that simple. So I just calculated a value in the 100th row of Pascal's triangle without knowing any of the values above it. And that's really, really helpful. Now, there's so much more I could say about C of n comma r and Pascal's triangle, but I'm going to hold off on sharing most of those comments for the next lesson. To close this lesson, I want to come back once more to how this material fits with algebra. It's very important that we make that connection. Remember that I asked you earlier in the lesson to expand x plus 1 to the 3 and x plus 1 to the 4, and then I hinted that the coefficients of these expansions were coming from the rows of Pascal's triangle. I can now state the mathematical fact which actually shows that this will happen. It's called the binomial theorem. And what I want to show you today is a special case of the binomial theorem. So here it is. I'm going to let n be some positive number. Then the binomial theorem says that x plus 1 raised to the nth power is equal to c of n comma 0 times x to the n plus c of n comma 1 times x to the n minus 1 plus c of n comma 2 times x to the n minus 2 plus ... c of n comma n minus 1 times x plus c of n comma n. Now notice that the coefficients in front of the powers of x are exactly the coefficients from the nth row of Pascal's triangle. We could actually state the theorem with more generality, but we will not need that fullest version of the theorem for our purposes in this course. So let's just stick with the version I just shared with you. It's actually going to provide us with plenty of mathematical power. So I now see how Pascal's triangle and algebra are so closely connected thanks to these factorials and this formula for c of n comma r and this binomial theorem. Let me use all of this information now that I've shared with you in this lesson to do one last algebra problem, okay? And here it is. I want us to expand x plus 1 to the 10th power. Now, without what I just shared with you today, this would take a long time to do by hand. Can you imagine multiplying x plus 1 times x plus 1 times x plus 1 10 times? It really would take a long time. But now that you know where the coefficients of this come from, they come from the 10th row of Pascal's triangle, this binomial expansion is actually easy to write down. So I'm going to suggest you try it yourself first. Expand x plus 1 to the 10th power. Just make sure you have Pascal's triangle built that far down before you do the expansion. Now, if you did this right, here's what you would have found. X plus 1 to the 10th is equal to 1x to the 10th plus 10x to the 9th plus 45x to the 8th plus 120x to the 7th plus 210x to the 6th plus 252x to the 5th plus 210x to the 4th plus 120x cubed plus 45x squared plus 10x plus 1. And all of those coefficients are simply read right off of the 10th row of Pascal's triangle. Or to find those coefficients, you could have used the formula for C of n comma r if you wanted. Either way, doing that problem of expanding x plus 1 to the 10th is really straightforward now that we know these facts about C of n comma r and the binomial theorem. Well, today I've introduced you to Pascal's triangle, and I showed you how the numbers in that triangle are very closely connected to the coefficients of certain powers of binomials, thanks to this fact called the binomial theorem. We also talked about factorials and how they can be used to build a formula for calculating the numbers in Pascal's triangle very quickly. This material provides a very nice link between algebra and this area of mathematics called combinatorics. Next time, we're going to continue with this theme by introducing the idea of permutations and combinations. It turns out that factorials will be essential in that conversation, and this formula for C of n comma r is also going to show up quite a bit in that lesson.